The next speaker will be Marion Louvel from the University of Münster. Marion is a high-pressure, high-temperature experimentalist whose research focuses on a better understanding of geological fluids and their role in subduction zone processes and ore deposit formation. She's currently a postdoc at the University of Münster in Germany, where she's been working on the hydrothermal transport of critical metals as rare earth elements and niobium. Marion?
Yes, good morning or good afternoon, depending where you are. So I'll share my screen.
Yes.
Yes, so you can hear me well?
Yes, perfect, thank you.
Good. Yeah, so thank you for the introduction, and especially thank you for the invitation, because I think it's a great opportunity for me to hear about the American community, and I hope you get interested by what we try to do in Europe to study high temperature fluids, and especially their role in ore forming deposits. So this is a very collaborative work that have been initiated mostly by Denis Testemal and Jean-Louis Yazman from the ERSRF synchrotron in France, together with collaborators from Australia and France. And I've joined their team since now almost 2 years in doing experiments in-situ XAS absorption with them. And now we also have some German collaborators, both from DESY and from Münster, who are joining our small community to study ore forming fluids. And so, building on the small introduction that Antonio gave this morning, I will not detail too much the X-ray absorption, spectroscopy analysis, and data treatment part, but especially focus on the challenge that it can be to study unquenchable high temperature fluids and sometimes melts in situ, and on some application about ore forming fluids. So first of all, I just wanted to give you a small introduction about why we are interested in those fluids. So at large, there are, of course, key players in, for instance, metamorphic processes or magmatic and volcanic processes. But what makes them particularly interesting, especially in terms of funding, for instance, is that they have a really big impact in ore forming processes and the development of geothermal energy. So they have an economical and societal impact. And so one thing to keep in mind for the rest of the talk is that when speaking about hydrothermal fluids, we are actually speaking about a wide range of fluid composition. So ideally, the crustal fluids will be modeled as a mixture of water, gas, mostly CO2, and salt, mostly NaCl. But depending on the environment, and especially in the case of ore forming processes, you can really end up with soups that will contain also high amounts of sulfur, fluorine, phosphorus, but also silica, and so on. And those fluids are exposed to quite varying temperature and pressure condition. And because of both their complexity, potential complexity in terms of composition, and the wide range of pressure and temperature conditions at which they circulate and play a role, they can have densities that are varying from very dense salty brines to low density gaseous phases. And so in terms of ore forming processes, why we are interested in hydrothermal fluids is quite easily summarized. Actually, the question we want to answer is how do we get from a source, being a rock or a magma, that is not especially enriched in metals, to newly formed minerals that are concentrated in a spatial location and that are really enriched to economical level in the minerals, in the metals. And so the big chemical control on this concentration process involving the fluids is, of course, the solubility of the metals and the minerals and the ore minerals in the high temperature fluids. So this depends a lot on the temperature at which the fluid circulates, with a lot of the ore minerals showing a prograde solubility, meaning that it increases with temperature. So when the fluids are actually cooling with interaction with rocks or other fluids, the decrease of solubility will cause the precipitation of the ore minerals. Another parameter that easily affects the solubility of the metals is, of course, pH, with changes in pH, for instance, due to mixing with meteoritic fluid, causing a decrease in solubility and precipitation of the metals. And the last parameters, which is the one we are actually mostly interested in the context of in-situ XAS in the fluid, is actually the effect of the composition on the solubility of the metals in the fluid. And indirectly, it's probing the effect of the different ligands that are present in solution as chloride, sulfur, or fluorine, and that can complex with metal in the high temperature fluid and thus change the solubility of the metals. And this is, for instance, a thing that has been nicely presented in the late years by Gleb Borowski from Toulouse, where he shows that to describe gold solubility in water as a function of temperature, so to reproduce his experimental solubility data, which are the red dots here, he could not use only the supposed main speciation of gold, which was gold hydrosulfide complexes, but he needed to think about another species that was stable at high temperature, and he could actually describe combining the in-situ X-ray absorption, solubility measurements, and in-situ Raman. He could show that there was actually the trisulfur radical S3- ion forming only under high temperature, and that the complexation of this special sulfur species with gold could actually enable to explain the solubility values he was getting at high temperature for gold in sulfur-bearing fluids. So this is what we are interested in doing with the in-situ X-ray absorption on high temperature fluids, determining solubility when we can, and especially speciation under high temperature and high pressure. And one of the issues we have actually with quantifying those two parameters is first that fluids, natural ones, are difficult to almost impossible to sample. So there is a quench as veins in the ore deposits. So you only see the solid leftovers of what the high pressure, high temperature fluids were. You can maybe sample them in a geothermal or volcanic system as high temperature fluid, but this will not represent the composition of the fluid at depth because of fluid rock interaction that may occur on the way to the surface. And the best samples are probably the fluid inclusion, which are aliquots of fluids that are trapped in minerals at high pressure, high temperature. But their composition is still sometimes very hard to reconstruct, especially when you start to deal with the ore-forming fluids, which have a complex composition, as I said before, not only involving water and CO2 and NaCl, but also sometimes some sulfate or carbonate, which makes determining the composition of the fluid at depth very complicated. The second issue we have is that fluids are also quite difficult to study in the lab, mostly because they cannot be quenched easily. So there has been some different techniques that have been developed by different teams around the world. Some of those include trapping the fluids, for instance, in diamond trap, in capsule, or as synthetic fluid inclusion. This gives, in general, a very good constraint about the composition of the fluid at high temperature and high pressure, but it doesn't allow to actually distinguish what may be the complexes that the metals are forming with ligands at IPT, or determine also, for instance, the density of the fluid, which is an important parameter if you want to better understand their circulation in the rocks. Other techniques also include batch reactor techniques where the fluids can be extracted, but it's quite good on the quantitative part to determine the solubility, but it's only giving indirect information about the complexes that are formed at high pressure and high temperature. So what we do as experimental petrologists using synchrotron science is actually use so-called in-situ technique that take advantage of devices that have high pressure windows that are transparent to X-ray, and as you will see in this case also visually transparent. So we can analyze both the concentration and the speciation of the metals in the fluids directly at high pressure and at high temperature of the processes we are trying to understand. So those techniques include the high temperature autoclave, which I will present to you in the rest of the talk, silica fused capillaries, where fluids are loaded in very thin silica tubes, and the hydrothermal diamond anvil cell, which I also use for the studies. And those three techniques all come with the advantages, as I say, that you can visualize your samples, so you can look at phase separation, for instance, between vapor and brine, and this has a huge influence, for instance, on the formation of porphyric or copper ore deposits. You can conduct X-ray absorption or fluorescence measurements to determine the solubility and speciation. And you can actually also couple the technique with Raman spectroscopy, more to look at volatile species, which are often too light to be analyzed at the synchrotron or at the structure of your fluids. However, each of these techniques also come with some disadvantages. And as I'm presenting the autoclave, I will I will detail those after. In considering the hydrothermal diamond anvil cell, they are not the best one, the best device to study ore forming fluids, because they're mostly unable to work above 5 to 10 kilobars, so quite high pressure, a bit deeper than the condition at which ore deposits are forming, or at which there can be a geothermal system interesting in terms of energy. And so the silica fused capillaries have kind of the same pressure temperature condition as the autoclave. So temperature going up to 500, 600 degrees. And what I would call for me superficial pressure, so below 1 to 2 kilobars. But in comparison to the autoclave, one of the difficult aspects is that say that the fluids need to be loaded in very small silica tubes. So you have a much more sample, a much smaller sample to analyze, and this is also more difficult for users, I think, to use. So to me, the high temperature autoclave is actually the ideal tool we can use to study hydrothermal ore forming processes with in-situ XAS at the synchrotron. So this is a picture of the device that is at the BM 16 and 30B beamline currently at the ESRF in France. So the device consists just of an high pressure vessel in which we put this sample tube, which is a vitreous carbon sample tube, 10 centimeter long. So as I said, it's quite easy to deal with and load a solution or solids in it. And then you can enclose your aqueous solution in the sample chamber with helium pressure. And the pistons here can move freely along the tube. So you can actually go up to pressure of about 1500 bars with a very high control of 1 to 2 bars on pressure you are applying on the aqueous sample. The temperature is then can then be increased to about 600 degrees, same with a good control on the temperature condition, thanks to copper or molybdenum resistive heaters that are here presented on the right. And again, some of the advantages would be that we have access to a quite large optical window, which you can see here on this picture. So you don't need to have access to a micro XAS facility. You can use a quite large beam. And for a bit more experienced user, it's also a device that is quite easy to unmount and repair, as you can see here with an example of Denis Testemal working on the cell. You can remove the parts quite easily and change them, and it's also quite cheap. Since 2 years, we also have the same kind of setup that has been installed at the P64 and P65 beamline at DESY in Germany. There, compared to what we have in Grenoble, where we have both diodes to get the transmitted XAS and a Canberra fluorescence detector to get spectra in fluorescence mode. At DESY for now, we only get information in transmitted mode, but I'm pretty confident that this will be solved in the next months. Also for now, as it's still a device that hasn't been built a long time ago, we are still a bit limited in terms of pressure and temperature, so more like 800 bars and 500 degrees C. But I think in the next 1 or 2 years, this will match the capabilities that there is at ESRF. So what we can do with the in-situ XAS in the autoclave is twofold. First, we can, of course, get information about the speciation of the metals, so all elements that will be above titanium KH, both recording XANES and XAF, and this enables us to get information about the complexes that the metals form in solution as a function, as you can see, of temperature, but also of fluid composition. And the second information we get from transmitted spectra is actually the concentration of the elements inside the high temperature fluids, just by using the Bird-Lambert law, which enable us to use the amplitude of the absorption edge for a given element, and we relate it to the concentration in solution. So ultimately, if we do that with precise amount of loaded solid material, we can get information about the solubility of all minerals in the high pressure, high temperature fluids. As I mentioned in the introduction, the device at ESRF is already in use since many years, so you can find actually quite a lot of reference if you want online to look at the different studies that have been conducted on different metals over the years. After this small introduction, I just wanted to go on about a small case study. So this is the latest we've done with my colleagues from Monash University, Joel Brugger and Barbara Reichmann, where we tried to understand the rare earth concentration process initiated by carbonatitic fluids. So as you probably know, rare earth elements are actually metals that have become of critical interest to the economic community because they are in use in green energy development, communication development, and so on. And so in terms of deposits, the ones that are currently mined are mostly the carbonatite ore deposits. And one of the things about the ore forming fluid is actually that we still do not understand exactly what is the composition of the fluid in carbonatitic associated with carbonatitic magma and rocks, and what is their effect on the rare earth behavior and concentration process. So from petrological work and fluid inclusion study, we know that they are the kind of soup that I just described before in the introduction that will contain high amount not only of chlorine, but also fluorine, carbonate, sulfate. And we also know that they probably have a pH that vary a lot depending on fluid rock interaction and the time of injection and so on. And up to now, a lot of the study focused on the fact that rare earths were highly soluble in very acidic fluids, chlorine-rich ones, so suggested that that was one of the best way to transport and concentrate rare earths. But there was a recent study by Annenberg et al. That showed that alkali-rich fluids, so rather of neutral to basic pH, could actually also enable a very nice mobilization of the rare earths and formation of the ore minerals that are formed that are actually found in carbonatitic system, such as fluorocarbonate, as bastnäsite, and so on. But while this is a very nice study in terms of metallogenic processes that has actually been already quite nicely received by the economic geology community, If we want to go a bit further with understanding the rare earth forming processes, it's important to start to quantify to which level the rare earth mobilization is enhanced to determine the solubility of the rare earth in those alkali and carbonate rich fluids, and how the rare earths are mobilized. So what is the nature of the complexes formed there? And so we haven't done, that's when we use the in-situ XAS in the autoclave. So for now, we haven't done a full solubility study about rare earths in carbonate and alkali-rich fluids, but we did do some preliminary experiments that confirm that high concentration of rare earths can be reached in the carbonate and alkali-rich fluid, close to that we find in HCl-rich fluid. We also see that there is there are differences between the heavy rare earths as terbium and the light rare earths as lanthanum, which would be mobilized differently. And it's actually the fact that the light rare earths are apparently better mobilized at high temperature, which is actually what we see in the field. What is more important is actually that we could also identify the rare earth complexes that are responsible for this high solubility of the rare earths in the alkali carbonate fluid. And if you look here at the XAS spectra, you can see here in the Fourier transform the spectra typical for ytterbium hydrated in HCl solutions. So ytterbium surrounded by 8 water molecules. And if you compare it to the Fourier transform we got for ytterbium in alkali carbonate solution, you can see that there are 2 peaks here that are really not occurring in the other spectra. And this is because the speciation is different. And from exact analysis of the data, we actually get a structure where there is not only oxygen in the first shell, but also some carbon atoms and some ytterbium and extra oxygen further away from the ytterbium complex. And so we could interpret this either as a mix of rare earth carbonate complex and rare earth hydrated atoms, but our preferred interpretation is actually the formation of polynuclear clusters of rare earth carbonate hydroxide, so quite large complexes. And so if we go back to the question about how would rare earths be transported by carbonatitic fluid, and take into consideration the fact that we actually have changes in the pH and in the presence of the different ligands, the step we are now at is that we actually need to add those new species to thermodynamic model so we can better model the concentration that there will be in the carbonatitic fluid with changing pH and with the presence of the different ligands. So to summarize, I just wanted to underline this review from my colleague Joel Brugger, where you can find all the in-situ XAS experiments that have been done since a bit more than 10 years. So up to now, there was basically all those metals. Now we also added, we are also adding some of the rare earths, also complexation, as I said, with sulfate and carbonate. But there are still some more experiments needed to better understand what is the speciation in alkaline fluids and what may be the geometry of mixed complexes. In terms of solubility, there are already quite good constraints on copper, gold, or molybdenum to high temperature, and as well as high field strength elements and rare earths. But for other metals, we are still developing, especially at DESY, new experiments. And if I can quickly just present one more slide, our next step will be to try to go to higher temperature, so reach especially the temperature of magmatic-hydrothermal ore deposits, such as the porphyry, copper, gold deposits, or most of the rare earths and niobium deposits, by going to temperature above 600 degrees. And for that, we just developed a new improved setup where we can melt glass. This is here a fluorescence map of molten melt equilibrated with the fluid. For now, we could only collect XAS spectra and get quantitative data in the fluid, so we still have to analyze the quench melt after the experiments, but I'm confident that in the next 2 years, we will have both in situ data depending on the elements we look at, also in the melt and in the fluid. and I leave you with some contacts if you are interested in the techniques. Thank you.
Great, thank you very much. Is there no questions yet in the chat? But oh, there's one question. So do you think it would be possible to measure XAS on trace elements in hematite in situ during reduction, of hematite to iron in a furnace under reducing conditions? If yes, do you know whether there are facilities in Europe that have such a furnace at the facility?
Yeah, so that would be, I think, extremely difficult because, well, right now we can probe quite easily the fluid that is at equilibrium with a solid, but to actually probe the surface only of a solid will be difficult. Yeah.
Okay, thank you very much. I think we'll have to move on.